So what are we talking about? Last time, we did sort of how to land a spaceship, which is one of my favorite topics, which is probably obvious. Uh, how to land a spaceship with convex optimization. Pretty great. So today we're going to do how to walk with also mostly convex optimization, some slightly non-convex things. And so to kind of ease us into this topic, which is also kind of fun and very recently topical, just kind of a little bit of history about legged locomotion and robotics generally. It's a fairly young, area, generally speaking. There were some legged robots built. I think the first ones that I know of were kind of in the 60s. And these are pretty scary looking. Like I don't have any good, there's some videos of these floating around that I have seen. I think Ford Motor Company or General Motors, one of the big car companies, built like a legged robot that like a human drove. It was like Transformer style, this massive thing that was like 20 feet tall with a person sitting inside it on top, like driving it, like a bunch of controls.
Like a mech suit.
Yeah. Like super, super scary, like, like sci-fi style, like Avatar or whatever, kind of vibes. So so one of the auto companies built these things in the 60s. I don't think it basically didn't go anywhere, but there is a prototype that was built that you can see videos of if you look around. That's slightly terrifying and kind of interesting. But there wasn't a lot of control there. It was basically piloted by a human operator. And then I would say so there's that stuff in the 60s, which is all kind of very mechanical hardware flavored, without like a lot of control. And then the first, I would say, kind of like in quotes, serious research on this stuff that's traceable to the modern era of like quadrupeds and humanoids that we see today really started in the 80s. And there's kind of two sort of like distinct lineages, I would say. Um, that kind of you can trace back from there to like kind of now. And they're sort of the following. So there's like sort of two big schools. The first one was sort of in Japan with Honda and Waseda University. And they were kind of some of the first people to really, really dig into humanoid robots. And they basically, all the control ideas there were essentially directly ported over from industrial robots, from industrial manipulators in particular. And so in particular, things like feedback linearization, and like basically what they did was try to treat the humanoid as like a fully actuated arm. They're using sort of the ideas, that they're standard on like robot arms. And this leads to very particular sorts of controllers that look a very particular way that like are what you would stereotypically think of as robotic looking. And we'll show some videos. So that's kind of one school that, yeah, more to say about that. And then the other school that was sort of pioneered by Mark Rabert, first at CMU, then at MIT in the leg lab. And then, as we all know, right, Boston Dynamics is kind of where that went. And so this started originally with hopping robots. And we'll see some videos in a sec. And the control methods here are very, very different. And like we're way ahead of their time in a lot of ways. So rather than kind of thinking about these things as like basically quasi-static robot arms, like in an industrial robot setting, the control focused on like deep insight into the like floating base dynamics of these things. They're under actuated, highly dynamic, and it's all about like reasoning about these dynamics. and yeah, trying to stabilize this weird kind of open loop unstable system. And yeah, I think a big term here is balance. Like think about balancing under actuation, stability, all these ideas. Whereas the like Honda humanoid stuff was really trying to treat the humanoid like a fixed base arm that was kind of like bolted to the ground and assumed to be, right? Yeah, let's look at some of this stuff. Where's my videos? So, what is going on there? Oh, it's behind that. That is annoying. Go away. I think, oh, that's because Zoom. No, still. Oh, it's still behind here. I feel old now when I have to do this crap and look stupid. Where is this going? Okay, there we go. That's very annoying. Okay, so here's some of the original like old Honda stuff. So there's a lot to say about the way they did the control on these things. Notice a few things in particular here. The legs always stay bent. The knees are always bent, and the feet, at least one foot, is always in like firm contact with the ground in all of these demos. So in particular, it can't run. It can walk fast, but it's always got like flat feet on the ground and knees bent, and it's always got at least one foot fully in contact with the ground. That's kind of very much part of the control scheme. So what they're doing there is basically models where they assume 1 foot in contact, and they basically assume that the foot is effectively like bolted to the floor. And then they model the whole robot from there up as a fully actuated, basically robot arm, like as a manipulator arm, and cancel out all the nonlinearities and all that stuff. It lets you use really simple control ideas from industrial manipulators, but it really, really limits what you can do. In particular, you can't jump, really run where you have a flight phase where both feet are off the ground. It can't reason about under actuation, essentially. And then, so historically, has anyone heard of Osimo in here, right? So this was really the state-of-the-art humanoid in the like early 2000s. So this line of work basically stretched from the 80s into the 2000s with Osimo. And as of like, I don't know, 2008 or so, that was the state-of-the-art in humanoid robots. And pretty impressive. This is sort of earlier versions of Osimo. This is what Osimo looked like. They worked on this stuff for like 30 years. It got pretty far. So yeah, this is like, say, late 90s, early 2000s Osimo kind of stuff right here. So super impressive for the time. Let's see if we zoom to the end, if there's some, yeah, so this is like late stage Osimo, like early 2000s, like where they got it to. Looks pretty cool. But yeah, in particular, that like very robotic looking walking is a result of the control strategy and kind of all the cancellation and assumptions they're making. Okay, let's contrast that with, this is the Rabert stuff, the leg lab stuff. So that's the original Rabert hopper. It's like basically a pogo stick robot, right? Like and it's like very much not doing what the Honda stuff is doing, right? So it's got a flight phase right out the gate. It's open loop unstable. Like if you turn the controller off, it will face plant. So it's kind of inherently unstable, highly dynamic, highly underactuated. And then what they did was they went from, one-legged hopper to a two-legged thing that could run, right? So this is like a planar biped. And as you see, they kind of like keep adding legs and kind of upping the ante here. There's some very cool stuff. So you get like way more dynamic behaviors. It's fast, it's agile. It can do kind of acrobatic stuff, which we'll see in a sec. Right, you can jump over stuff. There's some really cool one. Yeah, you can do flips. And this stuff, right? This was in the 80s. This is cool. This isn't like tethered, but 3D on a treadmill doing flips. Again, in the 80s, like ridiculous, considering also, the time and the compute limits and stuff. So this is like leveraging super deep insights into dynamics and like feedback control and stability and all kind of the stuff that we're kind of talking about here, right? I don't know. I love watching these things. They made some quadrupeds. There's a quadruped, but yeah, it's got this funny like trotting gait or whatever. The different gaits, right? So this is like, You know, all this stuff is like traceable to like the stuff we know now, right? This is like what grew into Boston Dynamics basically. But the seeds of it are from the 80s, and a lot of the key ideas came from that era, and it's just awesome. Cool. I don't know. I think that's all that stuff. And then yeah, if we kind of zoom forward a bunch, this is like MIT Cheetah from 3 years ago, which you guys have seen. And this is doing MPC, but using a lot of those Rabert ideas. In particular, a lot of the footstep placement kind of stuff that's on these quadrupeds still today is from that original Rabert stuff. It's called the Rabert heuristic. We'll talk about it in a little bit. So there's still kind of key ideas behind these modern MPC controllers that date back to the Rabert work in the 80s, which is kind of awesome. So yeah, these things, we know what these things can do. This is 5 years old now. A lot of the stuff though, a lot of the key ideas for Cheetah were, but yeah, note like this doesn't look that dissimilar from the Rabert stuff from the 80s, right? That Rabert quadruped was doing stuff kind of similar to this. A big part of the story here is way better hardware. Like some of the major innovations from Songbei Kim's lab that kind of really mattered here were actually the actuators. They kind of pioneered these kind of direct drive or quasi direct drive electric motors. So they made basically a big piece of the puzzle here is way better motors. They actually made like huge hardware advancements in addition to like, you know, the control stuff and everything, and all that, you know, is part of the story. So yeah, you guys have all seen this stuff. We've also seen the Boston Dynamics, you know, stuff in class. So maybe we'll play that stuff, but you kind of know what that looks like. All right. A little historical fun. It's probably about enough of that. So back to this work. Okay, please cooperate. All right, cool. So that's the kind of two things, say two schools of legged robots that like came kind of from the 80s and, you know, had long histories into the, yeah.
Is it those motor updates that allow them to be?
Not necessarily untethered, but like the motor stuff is really about like power density and this kind of thing, like getting a lot of torque out of a relatively small package. And also it's a big part of the control story. So previously, to do stuff like this, you would have needed relatively high gear ratios. And there's a word that people use called transparent here. Basically, if you have a high gear ratio, there's a bunch of backlash in the gearing, which causes problems. And then an even bigger deal is if you exert a force back on the foot and try to back drive the motor, high gear ratios mean that it's not very back drivable. Like you get kind of annoying stuff there, and you can't like passively push on the leg and have it spin the motor backward, basically, which is super important if you want to do like basically really high bandwidth stuff and also stuff that's like impedance force control kind of stuff where you want to have compliance when you hit the ground, which is kind of a big deal. So if you have a high gear ratio and the thing slams into the ground, it's probably going to break the transmission. Whereas if you have a low gear ratio or no gear ratio, direct drive, so low gear ratios are called quasi direct drive. Direct drive is the motor's hooked right up, you know, to the joint. In those situations, you can basically push on that foot and get nice passive compliance where the leg will freely move. That lets you do these kind of force control, impedance control ideas where you can, you know, basically have like drop the robot from a couple feet off the ground and like have compliance in the legs. So you can exert force with the motors to kind of cushion, but you're not going to like slam into the ground and have your gears go. So that's, I think, the main innovation there. That's a big deal, which is kind of subtle. Like backlash is a huge pain, and it's hard to model and makes controllers strictly worse. So yeah.
So there's a ton of humanoid techniques out there.
Yeah.
Do they also draw from this approach, or are they using?
Yeah. So basically, if you wanted to build a high performance legged robot, pre the Cheetah stuff, pre these innovations in motors, the answer was hydraulics, and this is why Atlas is hydraulic. So a lot of the newer humanoids are using like these quasi direct drive motor kind of ideas that originated really with Cheetah. So yeah, I'd say if you were designing a humanoid now, you'd probably use motors with like lower or no gear ratio. Whereas if you try to design a humanoid from scratch like 10, 15 years ago, you would have probably used hydraulics.
There's a complete section where they do like some hydraulic.
Yeah. Like hydraulics have definite pros. The major downside is they have like, they're horrendous to model. there's all kinds of weird nonlinearities that show up. There's delays, there's like just annoying stuff that happens, but they, yeah, like they can work. And as of like 10 years ago, they were definitely like the preferred option for something like a very agile, high torque humanoid robot. But that has changed in recent years, that the motors have gotten a lot better. All right, anybody else? Okay, so let's talk about so this is kind of the history, and I'd say like kind of past 10 years ish, uh kind of the cheetah stuff we just showed. There's been a lot of work, like I just said, on sort of like mechanical design and electrical design of these things. The hardware has come a long way. I think one of the underappreciated facts of the last 10 years, I was just saying like motors have come a huge way in like 10 years. Uh, and that's really enabled like a ton of new robotics things. And then also MPC for these things has gotten uh, you know, MPC for quadrupeds in particular, um, is basically a solved problem now. Like the cheetah control stack is now kind of the de facto standard. It's on kind of all these quadrupeds. Um, so that's cool. Uh, there's also, the Animal robot from ETH, and Spot. These guys are all doing MPC, and it's pretty mature. There's also been a ton of work on MPC for humanoids. A lot of this at Boston Dynamics, they're kind of doing MPC on Atlas. So a lot of the crazy parkour stuff that you see from them is all MPC. Um, so that's cool stuff. Fortunately, no one else has quite been able to like reproduce that and do quite as well as them. And then there's also been in the last, just like really only the last, I would say 2 years maybe, that RL has really made a dent in like locomotion. Like before, like I want to say like even 2021 maybe, like the RL was not competitive. Like there were a bunch of cartoony sim demos, but no one had really gotten an RL based policy to like really work in an impressive way on hardware. And that's completely changed like the last 2 years. Now it's like everywhere. Um, so that's been interesting to watch and pretty impressive. Frankly, there's some awesome results that have come out. Deepak being one of the main contributors in that space. So yeah, I don't know. There's hope for RL. We'll see where that goes. Cool. Any questions about any of this stuff? All right. So just to give like a high level picture of like what one of these control stacks looks like, and what we're going to talk about now is kind of focused specifically on sort of the standard-ish MPC stack that runs on these quadruped robots. Pretty much walk through kind of what the cheetah stack looks like, because that was kind of the original one that most of them are based off of, with slight variations. So we've got maybe a state estimator. Sensor stuff going in there. From there, there's so the state estimator is generally in these systems estimating the body position and attitude. So the pose of the body. Usually the joint states are not in the state estimator, they're not in the filter. Usually those are just kind of read right out of the joint encoders on these things. So you'll have the joint encoders as well. This will all go into there's the control stack for these is kind of gnarly and complicated for reasons we'll get into. There's a few pieces. One piece is a so-called gait planner or footstep planner. And this is kind of related to some of the stuff we covered about hybrid methods for legged locomotion. These methods are pretty much universally hybrid in the sense that the MPC controller is not really reasoning over the contact modes itself. It's getting the contact modes provided to it by this gait or footstep planner. that's using heuristics or whatever to basically say, oh, you should trot. Here's the ordering of your footsteps for a trot, that kind of thing. So that stuff is fed into then a couple different pieces. There's a swing leg controller. Just a little bit smaller. Okay, so we've got from there a couple different things. So from the footstep planner is going to spit out a swing leg trajectory. So for any of the feet that are not in contact, the gait planner basically says what it should be doing during this like swing phase when it's in the air. The gait and footstep planner is also spitting out basically the contact modes for the feet. So for the feet that are not in contact, it spits out the swing leg trajectory. For the feet that are in contact, it spits out, a contact flag. And that goes into the MPC controller. Sorry. Oh. And this MPC controller is really just reasoning about the body as a rigid body. It's basically ignoring the leg dynamics. So this thing basically says, okay, I know that these feet are in contact. By having those feet in contact, I can exert some wrench on the body. Those feet, based on where they are and the motor torque limits and the kinematics, give me access to some force and torque wrench that I can exert on the body. So the MPC controller is really just reasoning over the body dynamics and then saying, okay, based on the constraints imposed on me by the contact mode, I can produce this force and torque. So it's optimizing over force and torque applied on the body, generated by the legs. And all of that then goes into this joint controller. So what this is doing then is it's taking, for the swing legs, it's just trying to track this open loop swing leg trajectory that's coming from the gait planner. And for the body, it's trying, for the contact feet, it's taking the force and torque specified by the MPC controller and then actually trying to produce that with the motors on the stance feet, which involves some kind of inverse dynamics calculation, basically saying, okay, here's what the joint angles are right now. Here's the kinematic Jacobian, maybe motor constraints, et cetera. And I'm going to try to get as close to that desired wrench as I can, given where the feet are on the motors and all that kind of stuff. That often, by the way, involves solving another optimization problem. Often that problem is formulated as another QP. So there's a few different QPs in here sometimes. And then finally, out of this thing will come motor torques. And then this goes actually on the robot. Oops. And then the whole thing gets fed back. We have sensors. So you got joint encoders, et cetera, et cetera. Goes back to the state estimator. And that's kind of it. Okay, questions about this? It's sort of a complicated beast, so we'll dig in a little bit.
The state estimation.
It's so there's sort of two things going on usually. There's a for the joint angles, you get those from encoders, and usually they're just, that's it. You take the encoder measurements. What the state estimator is usually doing is taking information from the joint encoders and any other measurements you have, maybe GPS, maybe IMU, et cetera, and running what's called an inertial filter. So it's basically trying to estimate the body pose in like some world frame. There's many variations on this. You can do it with, inertial sensing and GPS and joint encoding, joint kinematics. You can use vision to do it, in which case it's called visual inertial odometry. Kind of whatever combination of sensors you want, you can kind of write a Kalman filter typically that will fuse those things. So it turns out that doesn't show up here, because what you're doing is you're just reasoning about the body pose and you have all this other information. So to reason about body pose, all I really care about there is the orientation of the body and its position, right? And so for that stuff, I have encoder information from the legs that I can basically integrate up into some kind of displacement or velocity estimate. And I might have, the IMU that's telling me things like angular velocity and acceleration information. I can use the acceleration information, to estimate a gravity vector, which tells me something about my orientation. I can use the angular velocity to estimate attitude dynamics. Then you need something else as well. So that something else can be some combination of, vectors coming from camera, from vision stuff, can be GPS. So you're kind of really what that state estimator is doing is basically just integrating a whole bunch of measurements of position orientation and velocities to get you a good statistically consistent estimate of the body pose. Yeah, I mean, most of these are UKF. There's definitely fancier things you can do, but EKFs are very standard. Yeah.
Skills for the body, like don't know the force applied to.
You don't need to though, because here's another way to think about it. Those measurements tend to be quite bad. Similarly, like whereas like your say position measurements from vision or GPS are like relatively good. This actually shows up in a lot of different contexts. Inertial filtering is weird, basically. Also IMUs tend to be quite good. In particular, gyros are very good. So rather than have like a Newton-Euler dynamics where you have like, say the, Euler attitude dynamics and torques and all this stuff in there, it turns out you're better off just integrating your gyro. So the gyro measurements are very clean and very high quality. So you don't really need to, basically the filter state is just the pose typically, maybe the attitude, position, and velocity, linear velocity. You generally don't have your angular velocity in particular in the filter state. You assume the gyro is very good and you just throw that in there. Yeah, you use typically whatever you can, like GPS vision, mocap, whatever, to get, and you fuse that with IMU, whatever other information you have. Contact does play into this in various ways. Like typically where that shows up is in leg odometry. So often what you're doing here is you're using those leg joint encoders and knowledge of the kinematics to produce like a velocity estimate. So based on, if my encoders are doing this and I have my joint angles, I can figure out what the body velocity should be, right? And yeah, so in order to do that, that velocity estimate is only valid for feet that are in sticking contact with the ground, right? And that ends up being tricky because foot slip will also mess this up. So we've done some work on this in my lab. This has now gotten into a very, so yeah, contact sensing becomes important. Slip detection becomes important. And we have a paper from like last year that tried to like do a better job of estimating foot slip by putting IMUs in the feet. And it turns out by looking at the body IMU and the leg kinematics, you can kind of look at what the body IMU says and like kind of propagate that down to the foot using the kinematics, the encoder information, and say, okay, well, if the foot's sticking, it should say this. If it's, and if it doesn't, if it disagrees with that estimate, then you're slipping basically, or you're not in context. So you can compare the foot IMU with the body IMU and the leg kinematics to get like a good estimate of foot slip, which is quite useful for this kind of stuff.
Foot is linked to the body.
Yes.
If I have a post estimation of the body, it's very easy.
Because I want to know if, so your IMU gives you acceleration information. It doesn't give you velocity information, right? And I want to take the velocity estimate from my joint encoders, but for that to be valid, the foot has to be stuck to the ground, right? Basically what I'm doing is I'm saying the joint encoders say the leg is moving this fast, right? The tip of the leg is moving this fast relative to the body. For that to be the body velocity, you have to assume the foot's stuck to the ground. If it's not stuck to the ground, that has nothing to do with the body velocity. If it's just doing this in the air, right? See what I'm saying? So you need to know confidently that the foot is stuck on the ground for that kinematic information to sort of be highly correlated with the body velocity. And foot slip messes that up. And that's traditionally pretty hard to detect. So the foot IMUs are there to detect. Okay, this got sort of way off topic. Sorry. Okay, so let's see, stuff about this. What sensors are on this guy? You've got joint encoders. You have a body IMU, maybe more IMUs if you do weird things like we've done. Often you have contact force sensors in the feet. Usually those are really dumb, simple pressure sensors, and they're kind of noisy and bad. And then you might have, vision and or GPS as well. The state estimator, as we are just saying, is typically some kind of EKF. That's with lots of extra tricks, basically. Kind of for reasoning about contact and foot slip, which we just talked about in some greater detail. Cool. Let's see. So that's the state estimator. This gait and footstep planning kind of thing. What's that all about? This is basically planning placement and timing of footsteps. And also swing leg trajectories. And this is basically just heuristic. So you might write down like some pre-specified gait, like a trot or gallop or something. And this might change, based on the body velocity. You might switch gaits or whatever. And often, there's separate kind of push recovery heuristics in here. If you hit a big disturbance, there's all kinds of weird stuff. But generally speaking, that's like kind of hand-tuned voodoo stuff that isn't, is mostly heuristic. Then the MPC controller is basically treating the robot as a single rigid body. And assumes the foot contacts given by the gait planner. To get contact forces. And then that last block there, the joint controller. This is actually generating motor torque commands to produce desired force and torque that the MPC wants. And the desired swing leg trajectory that the gait planner wants. And typically the force and torque stuff, you're getting out by doing some inverse dynamics calculations. You say, okay, here's where my feet are, here's my kinematic Jacobian, whatever. And then here's the desired, wrench on the body. You can either use your kinematic Jacobian in a like pretty basic way, or you can solve a little QP there to get the motor torques that should produce that desired body sort of wrench. And the reason to do it with a QP is maybe, the motors can't actually do that. So you want to solve a little least squares problem with like motor torque limits and things like that. And then the swing leg trajectory part that's usually just done with like PD control. So you're just trying to track say the leg foot position in 3D with like kind of stiff PD feedback on whatever desired trajectory is coming out of your gait planner. So that tends to be pretty basic. Yeah, so this is pretty complicated, I would say overall, and like has a lot of tricks. And in general, it's like a lot of moving parts to kind of put together to make one of these work. Um, and I think a lot of the structure here and kind of why it looks the way it is at its root is basically like tricks for getting around the nastiness associated with contact. So you're basically, solving a hybrid problem, use this gait planner thing to like reason about foot contact so that the NPC doesn't have to. And then that kind of like leads to this weird split structure, right? Yeah.
So does the body basically compute how much force you want each limb to exert, like on the ground?
Yeah, in principle, yes. It's a little bit, it's like one layer removed from that. So what it's basically thinking is I have this body that's just like this, it has no legs, whatever. And it has access to this constrained set of forces and torques that comes from the foot contacts, but it doesn't really know about those, right? It basically has a set of constraints on what forces and torques it can generate that's set based on the foot contacts. That comes from the gait planner though. So the NPC really just, you can think about it almost like just a hovering rigid body with some force and torque input that has constraints on it. And that's what it thinks about. So it's generating a history over the MPC horizon of like forces and torques that should be feasible given where the legs should be, right? So it spits out this desired force and torque that should be consistent with what the gait planner, says the feet are doing. And then that joint controller actually takes that net force and torque on the body and turns it into leg motor commands for solving a second problem. So it's all kind of weird and complicated. Yeah.
Question on so like when this is all happening, like is every single mode of contact just always assumed to be like pretty much this like fixed static
So yeah, you can have friction cone constraints. We'll talk a little bit more about this. So there are constraints on how much force the motors can exert, and there's constraints on friction, and those are kind of baked in and accounted for in the MPC control. So it knows about at a basic level, it knows about friction limits. It tries to not slip. So there's a friction cone constraint in there. And then there's some notion of, the maximum motor capability in there as well. That tends to be pretty conservative. And yeah, it basically this gait planner is spitting out like a planned contact sequence over the whole MPC horizon, and that's just fixed in the MPC controller. Then if anything bad happens and you have to deviate from that plan, that kind of happens at the footstep planner level. There's a bunch of heuristics, and then it just repeats. All right, so that's that. So let's talk a little bit about dynamics in here. And ultimately, like what sort of approximations are going on to make this look like a QP. This is going to end up essentially being like rigid body dynamics, and the full state might look something like this. We've got some like kind of pose thing and velocity thing. So this is like maybe the general case, right, of what you would do if you were simulating this. You'd have like body position, body attitude, maybe like a quaternion, and then like joint angles. So like the full pose of the robot. And then like the velocities, Q dots or whatever, maybe slightly different depending on your attitude choice. This whole nest can be written down using like the manipulator dynamics with some extra stuff, which we'll talk about real quick. So mass matrix, that's the acceleration. Let me label these things maybe. So I think most of you guys have seen this if you've taken like KDC, what this stuff looks like. Then you'll have this sort of Coriolis term or dynamics bias term, whatever you want to call it. So this is where your sort of weird nonlinear Coriolis and gravity stuff happen. And then on the right-hand side, this is where it gets maybe relevant to us. So there's the the input Jacobian, and then these are the joint torques. And then finally, this is where the contact forces show up. So you've got some contact Jacobian, and then these guys are your contact forces. And this is kind of part of why this is a hard problem. So like one way to think about this, right? Like just given joint torques, I can't really directly affect the pose of the body like instantaneously, right? Like instantaneously right now, that B only gives me access to it, like BU, like that's basically a bunch of zeros, and then like maybe like an identity thing at the bottom for the joint angles, right? I have joint torques that I can specify. So the whole, if I want to make the robot move from here to there, I can't do it directly with joint control. The only way I can do it is by messing with these contact forces. Those are the only ways I can like access, I can impact the body position and attitude pose, right? So at some level, like reasoning about contact forces is like completely necessary to do anything useful with one of these robots. And that's, as we've seen, it's super messy and annoying. So on top of this, like stuff we've seen, maybe you've got this sign distance function that looks like, so this is your interpenetration constraint. And this whole thing is interpenetration. And then you have also a friction cone constraint. So if I were to like look at say 1 foot contact, I might have something like, so for 1 foot, I've got a 3D, force that can be applied there. If I write it in, like, for being reasonable about choosing coordinate frames, and I make like, say the third component, the normal component, and then the first and second components, the tangential components, I'd have something that looks kind of like this, where like the second and third components, the tangential components, have to be less than equal to mu times the normal component. And so this whole thing's a friction cone, which we've seen before. So this is more or less the full nonlinear dynamics for a quadruped. This is like, if I wanted to like make a reasonable simulator, this is what I'd end up with. I'd have to simulate all this mess with those inequalities and everything. This looks kind of bad. Looks that cool. So this is very messy. And you don't really want to use this in your online controller. What else to say? The state dimension is kind of big here also, is another thing to say. So for something like Cheetah, this is something like 36 dimensional state vector. Does anyone remember how Trajopt scales, how that MPC problem scales with state dimension? Cubically. So like 36 cubes big, especially if we're thinking like, for a single rigid body, it's like 12. So 36 cubed is a lot bigger than 12 cubed. And that makes like a very big difference in how much how expensive these problems are to solve online. So this is, again, like a reason you might want to simplify things down and make them lower dimensional. And finally, this is highly nonlinear and non-smooth. All of these are bad things. Okay, so hopefully that message is clear. Nasty, bad, complicated. So what is standard in these MPC controllers is a sort of single rigid body model, which is sometimes called the centroidal dynamics. Okay, so there's some assumptions here that like go into this that sort of you might want to keep in mind when you write one of these things or think about the limitations of these things. So first is that you're basically assuming the leg mass or inertia is much less than the body. And for typical quadrupeds, the total leg mass is on the order of like 10% of the total body mass. So for something like cheetah, that's about right. And so that's like, basically not a horrible assumption, right? It's accurate at the 90% level. And that's pretty good. And then the second big assumption here is that the leg actuators are very fast compared to the body motion. Basically, you need to be able to like swing that leg around and like, kind of do things with the legs really, really quickly in order for some of these assumptions to hold up. Like, because you're basically assuming massless legs in this, right? Is one way to think about it. And you're assuming, another way of saying this, the MPC controller is assuming you can like basically instantaneously get force and torque, which might require moving the leg somewhere. So you got to be able to move that leg really fast compared to like the body dynamics. Okay, so yeah, that second one is actually kind of interesting if you pay attention to how these robots are designed. Like a lot of them put all the motors in the body and then use like transmissions for the legs. So that makes the legs low inertia and like easy to move around and fast and all that kind of stuff, and puts most of the mass in the body. Yeah. Yeah.
So why do they choose that?
So you can do that, but it makes the control problem a little harder. It makes some of these assumptions less valid. And so they have, in particular, some pretty sophisticated MPC stuff that goes beyond what I'm showing you here. I don't know. It's a good question. They might be gaining some transparency, like by getting rid of the transmission, which might be a good thing. There might be some mass advantages. They're simplifying. They don't need a transmission, right? If you put the motors all up here, now you need a transmission to get down the leg. So by putting the motor at the elbow joint, they don't have a transmission anymore.
Also, that their leg, like the joint is different. Like for a dog, it should be like it's two, like, it should be like this, but theirs is like.
I think it goes both ways. I think they have. Yeah, I don't know. I believe that those actuators don't have a hard stop there. I think they go, like they can bend, they can keep bending. You can go all the way to the stop. So I think that's maybe more a property of the gate that they're running. Yeah.
Spring systems on the feet that would like help with propelling, or
Not so much in the feet, but there's been a ton of work on what are called series elastic and parallel elastic actuators. So, in particular, Cassie, which is a humanoid that was built by Agility before their new Digit one. I don't know if Digit has it anymore, but Cassie had big springs in the legs at sort of effectively at the knee joint that, yeah, are giving you some amount of like passive compliance. And there's a bunch of arguments. This is a major topic in the legged robot community for a long time, like parallel versus series elasticity, and like kind of this idea of like using the passive spring stuff to improve energy efficiency and stuff like this. I think this is, it's still, like as of like even just like 5 years ago, the Cassie robots had these things, and those are still kicking around. I think as motors get better and better, the argument for doing that becomes less and less prevalent. But yeah, I think it's still kind of an open thing. I think it depends a lot on how good your actuators are. Because in principle, if the motors are super, super good and super, super efficient and high torque and fast, high bandwidth, then you can basically emulate that spring. That spring is just basically proportional control, right? So I think it really depends on how good the motors are. The downside there is basically your motor can act like any spring constant, right? Just like a proportional gain, whereas the physical spring is kind of fixing that spring constant in hardware in ways that like kind of end up inevitably favoring a single gait. So like that spring stiffness, you kind of end up wanting to tune that to optimize for a particular, say, running gait, like gait frequency and stuff like this, which, you could probably make that one gait at that one gait frequency super efficient by dialing that spring in, but it's maybe not going to be as general and not going to be as good. It's basically make everything else worse, a little worse, right? And if you can just do it with the motor, that may be a better deal. Yeah. All right. So let's see. Okay. So what we're going to do now is use kind of a lumped single rigid body model for the whole robot. So that ends up looking really simple and like stuff we've seen before. The thing that always kind of fascinates me here is like how simple the MPC controllers look like for like a drone versus a quadruped versus like they're so similar. Okay, so this is the position part of the dynamics. It's F equals ma, and then this is just sum of your contact forces. And then you've got attitude dynamics, which is Euler's equation, which we've seen before, you know, for drones and stuff. So that looks like this. And then over here, you've got sum of torques. And so this just looks like R cross F, where this R is the foot position in the body frame, basically. Remember, Euler's equation is always in the body frame, right? So you have that stuff. Looks exactly like a drone. You just replaced foot forces with thruster, you know, forces from your propellers. And then you've got the kinematics here. So you might have, you know, positions easy, and then say you use a quaternion for your attitude. That might look like this. And that's kind of the whole thing. So this is nonlinear still, but it's way, way cleaner and nicer and like closer to being linear than what we had before. And there's a few more moves that you make though, typically, and some this is where you get into some variations on these things. Some controllers linearize everything, some keep the attitude dynamics or kinematics nonlinear. This varies a little bit more between implementations, but there's a few more assumptions. Okay, so more assumptions. One, so if the body angular velocities are small, and then we can get rid of this term, right? So if omega is small, that's omega squared. It's tiny, so we can throw that out. Another one that shows up very commonly is that the body pitch and roll are small. What that lets us do is linearize these quaternion kinematics and kind of use simpler stuff there. So we only really have to reason about basically a big yaw angle, but then we can linearize about pitch and roll.
What do you do if you wanted to do like a forward flip?
You got to do something more complicated. So you basically, in that case, you wouldn't want to make this assumption. What I'm describing now are like standard assumptions that are in like most of these controllers for like walking around where, you know. But if you want to do crazy acrobatic stuff where you cared about doing backflips, you wouldn't want to do that. Essentially.
A situation where you would assume these for as long as you need to, and then when you decided to do like crazy aerobatics and stuff, then you would.
I mean, if you're going to bite off the, say, full attitude dynamics and kinematics if you can do it, you might as well just do it. I don't know that it makes sense. You could, if you were being hacky about it, you could like, you know, make some hacky special case things for the backflip. But if you're doing it the right way, then you would probably just do it, you know, and leave it in there. And then the last one that's important is that the foot positions track the reference like nearly exactly. Okay, so if we do that, that does a few things for us. So now we've got the position dynamics were already pretty nice. So that didn't matter too much. So it didn't do anything to this equation. The attitude dynamics, we just talked about how we get rid of the omega cross j omega term because we assume small body rates. The other thing, the number 5, this is where this last one, assuming the foot positions are basically where the planner says they are. What that lets us do is take this guy, this R cross F. So this guy depends on joint kinematics, right? Like this is R as a function of all the Q's for the joint angles, and that could be time varying and all that kind of stuff. If we assume that our reference tracking for the legs is perfect, then we just assume that R is known over the MPC horizon from the gait planner. And so then we can take that whole R cross F thing and assume it's a fixed R, which we can pre-calculate as this matrix big R. And so this becomes now like a fixed thing. So this gets linearized, basically. So this is basically this cross product hat matrix that we've talked about. Just assuming the reference. Steps. So you're depending on that tracking being good, basically. And then the other stuff, we've got position kinematics. That was easy already. And then for the attitude stuff, if you do the sort of small angle assumption in pitch and roll, then you can kind of make some assumptions here and use some 3-parameter attitude representation that's like, kind of whatever you want, but, people tend to use things like roll, pitch, yaw. It turns out that you can get away with this with one big angle. Like it's okay if you do things right. There's still some gotchas with angle wraparound, but it's benign. If only one of the angles is big, it's okay. If 2 angles are big, you're hosed. So that's kind of where the small pitch and roll comes in. You can have big yaw, which is then this all kind of works out. Okay, so you do this. We basically linearized everything. And now our dynamics can be written like so. So I'm going to have position, orientation, velocity, angular velocity, all that good stuff. Our dynamics look almost trivial now. We end up with like integrator dynamics in our A matrix. So we're just integrating up the velocities. Let me do that later. And then we've got an input that's coming from the contact forces, where you're just adding up all the forces from all 4 feet for the forces. And then for the torques, you've got this like cross product thing for all 4 feet. And then your inputs, as far as the MPC controller is concerned, are the foot forces. So these Fs stacked up. So you've got x dot equals ax plus bu. We're in our like standard linear system form that we know and love. So remember, these are given by the footstep planner. And then we have, based on the footstep planner, we have constraints that show up in the QP that say, over the horizon, which Fs have to be 0 or not based on swing leg or stance legs. So yeah, let's write that down. So this is specifying mode timing for the feet. And so like over your MPC horizon, this might look something like, you can draw like a mode plot. So this might be T. You might have, the 4 feet versus time, sort of like something that looks like this, where this might be, front left, front right, back left, back right. And then you'd basically turn that into, so say that's your MPC horizon, you'd have constraints on the Fs as a function of time, where some would have to be 0 at certain time steps. And you can basically turn them on and off in the MPC controller that way. That makes sense, everybody? Yeah.
There is a force applied to the body or the force applied to the feet.
It's the force generated by each foot. It's the contact force generated by each foot.
5 points. Vision.
Is wherever the foot is. So that's what that R thing is doing.
Is it on the things, or it's just
at the foot? Yeah. So this is not reasoning about the leg kinematics or the joint torques. It's just saying the foot's in contact at this time, and I can generate the following force with that foot in contact with the ground. So you basically have it has to be 0 if it's in flight phase. If it's on the ground, then the Z component can only be positive, And then the X and Y components are constrained by the friction cone, which is baked into the QP.
Our machine series keep changing.
It is, yep. But given a fixed footstep plan, if you assume that that footstep plan is true, then you know it ahead of time. That's what's going on.
If you relax, even if you let it skate around, it's joint angle is changing. So
The joint angles can change. That's okay.
yeah, I guess the our mission here is also changing.
It is, but you know it ahead of time. That's the point. Like, so based on the gate plan, I basically know what that R is based on, this.
Yeah, but you don't really your body position, right?
I know it well enough. Basically, like there's some nominal like trotting gait that specifies where the foot is in the body frame as a function of time. So I'm assuming that I'm staying close enough to that trotting gait that those R's are good enough, which is not, you're right. This is an assumption that can be violated, but it's close enough, it turns out, that I can basically pre-compute those R's over my MPC horizon. The MPC horizon, also keep in mind, it's like 2 seconds. It's pretty short. And yeah, so if things change, you just fix it in the next MPC solve. And part of the game here is you're solving these problems really fast, so you can be reactive.
So this R is not changing all the time. This is an assumption. This is all.
In practice, the R does change. It changes over time, but in the implementation, it is time varying. This is a linear time varying system. So you say, I'm going to look forward a few seconds. I have this gate planner that's telling me what that R is going to be as a function of time into the future. I just assume that reality matches the plan. So I can write it down, over the time horizon based on the plan. The plan might be wrong, but we're assuming that realities end up being close enough to the plan that this holds up well enough.
The idea is that you specify gates, the graph here, you can.
So it's not just the graph. This is the contact mode time, which says whether F can be 0 or not. There's more to it. It's also specifying the leg trajectory in the body frame. So it's telling you where the foot is in the body frame for the entire gait cycle. That's part of the plan. Yes, in the body frame, which is what matters. That's what that R is telling you. That R is literally R cross F in the body frame. So it's the foot position. It's the cross product of foot position with center of mass, position, like that R, the vector from the center of mass to the foot. And then the applied force F. That R cross F gives you the torque on the body.
So in the gate planner, joint position.
It's giving you a nominal plan that you're trying to track. Okay. And then I promised this Rabert thing. So there's this question of where to put your feet. When you are putting your feet. So this gives you mode timing. The positioning of the foot is like kind of an open question, and this gate planner has to do it somehow, right? So there's a standard technique that's still widely used that's called the Rabert heuristic. It says the following thing that kind of makes sense if you think about it a little bit. The foot position should be equal to the hip position plus if you take your current velocity and your gait period, this thing. So this is your gait period over here. It's delta t. And so what this is saying is, if my body is going to move, my body over one gait cycle, my body will move delta t times v body, if you're assuming moving at constant velocity. So what this is saying is, based on where I am right now, I should put my foot halfway to where my body's going to end up at the end of the gait cycle. What that results in is a symmetric gait. So it says, I'm going to stick my foot this far ahead of me when I put it down. And if I keep moving at constant velocity, it's going to end up that amount behind me at the end of the gait cycle. And I repeat. So it just gives you a symmetric gait, basically, in the forward-backward direction. It makes sense, right? Intuitively. So that's what that is. And it's basically still in most of these MPC controllers. And then let's see, we're kind of just about out of time. This is, let's finish this up maybe. We mentioned PD control for the joints. Maybe I'll just recap like kind of what the MPC controller looks like. You're trying to track desired body motion. Horizon is typically like 1 or 2 gait periods. And basically with those linearized dynamics that we wrote down, this ends up being a convex problem. And sort of typically it's a QP. You've got min over your X and U trajectories, like we've seen a million times. You've got a quadratic cost function. So you might have like your reference in here. You've got a U reference maybe. So this is all stuff we've seen a million times, basically LQR problem. There's our linearized dynamics. And then the additional thing here you'll have is a friction cone constraint. So remember, these U's are the foot forces, or the F's from before. So you'll have something like this. Friction coefficient, U1. So as written here, this is a second order cone program, which we can solve. But it turns out most of the implementations linearize the friction cone and turn it into a friction pyramid, which we also talked about when we talked about Leggett stuff. Let's see, what else should we say about this? Couple notes on this. One is it's difficult to actually strictly enforce torque limits, motor torque limits in here, because the joint kinematics don't show up. So usually what you'll do is you'll put some like conservative bounds on the U's here that you're confident you can hit with your torques in practice. But yeah, I can't put like joint limits or torque limits on here because they don't show up in the problem. And then yeah, there's a bunch of extra tricks in here. Like people will put in like heuristics for push recovery, foot slip, all kinds of other things. So in practice, these control stacks get really complicated and full of like annoying, weird heuristics. Yeah, with that, we are done for today. Check back in on Thursday for how to drive.